So start your session.
Hello and welcome to the first live session of our NPTEL course Mechanism and Robot Kinematics. My name is Anirvan Dasgupta. I'm from the Department of Mechanical Engineering at IIT Kharagpur. So this is our first live session in this course. I hope you are able to view and work on this course as desired without any hindrance, without any problem. Um, if you have any questions for today, if you want to interact, you can write onto the chat box, or you can also write on the Google spreadsheet which has been shared with you. So we will try to address it here, and if the answer takes more time, then we will share it on the regular forum. We are into the fourth week of this course now. Um, Let me just go through a little bit what we have discussed till now. Um, we started off with the introduction video in which the nomenclature, etc., all these things were discussed, the motivation for studying this course. So these things were discussed. And then in the second video, we were discussing about the nomenclature that we use to uh, designate different parts of the mechanism, if you would like what are links, classification of links as binary, ternary, etc. So we had done, we went through this nomenclature. We discussed about various kinds of kinematic pairs, like the simplest being the revolute pair. This is also known as the hinge R pair, prismatic pair, the P pair, and then we went on to more complicated pairs like the spheric pair, the cylindric pair, screw pair, and we also classified uh, the kinematic pairs as a higher pair and a lower pair, depending on whether it's a point or a line contact. In the case of a higher pair, in the case of a lower pair, it's an area contact. So we classified this, and these things are important when we try to understand the behavior of mechanisms. So then we discussed about the pair variables, which means it's the degree of freedom allowed by the kinematic pair. For example, a revolute pair allows us one degree of freedom. So we at that time we use the term pair variable. So how many pair variables are there? That means how many variables you must fix in order to completely immobilize the kinematic pair. And you know the term kinematic pair, why it's called a pair? Because it's between two links or two rigid bodies. So it pairs rigid bodies. And the pair variable reflects how many variables you must fix in order to completely immobilize. For example, in a spheric pair, you have to immobilize. There are three pair variables. In a cylindric pair, there are two pair variables. In a prismatic pair, there is one pair variable. In a screw pair, there is one pair variable. So if you specify one pair variable in a revolute pair, then it gets immobilized. So basically, this is known as the joint angle. So if you specify the joint angle, then that kinematic, that revolute pair gets fixed. Now this idea will be used in the degree of freedom calculation, which is discussed in the next weeks. So in this nomenclature, we have discussed about this. We have discussed about what are constrained mechanisms, what are open kinematic chains, closed kinematic chains. different kinds of links, binary, ternary, quaternary, singular link. So these concepts we discussed in the third lecture. I discussed about kinematic diagrams. This is the first step. Drawing the kinematic diagram is the first step in understanding uh, the arrangement of links and joints. Now, this is very important when we come to a degree of freedom, which is the next lecture in this week, in the first week. So we used this kinematic diagram to find out how many links are there, how many joints are there. So that gives us an idea of the structure of the mechanism, the topology of the mechanism. And from there, we can calculate the degree of freedom of the mechanism, and it also allows us to visualize, to compare mechanisms. uh, so the kinematic diagram, because sometimes in a practical situation the actual mechanism might look extremely complicated, but its kinematic diagram, if you can draw the kinematic diagram, that means you are uh, essentially drawing the basic uh, structure, the topology, forgetting about the dimensions of the mechanism, of the links. So it just gives you connectivity and degree of freedom calculation, which we have done next. So in the fourth lecture, we discussed about the degree of freedom calculation, and we started off with planar chains, and I have shown you how the formula for the degree of freedom calculation comes about. So we consider that, say, in a planar mechanism, the a link will have 3 degrees of freedom in a plane, and if you have n links, then we actually have 3 into n degrees of freedom. But as you know, in a mechanism, one link is always fixed, so it was 3 into n minus 1. And then we considered that every kinematic pair takes away all the degrees of freedom, so minus 3 times number of joints, plus we added the degree of freedom of each joint. Now degree of freedom of each joint we understand from the pair variable. How many pair variables are there? So that is why understanding the pair variables is so important. So we discussed about degree of freedom. In the second week, we started off with the failure of degree of freedom calculation. The degree of freedom calculation, if you think about it, it just takes into account the links and the joint arrangement that we get from the kinematic diagram. It doesn't worry about, or it doesn't take into account the dimensions of the link, the geometry of the mechanism or the links. So we found in this lecture that the degree of freedom calculation fails under certain conditions. Say, for example, it fails for special geometry, and I have taken that example of 2 friction disks. So if you do a calculation of 2 friction disks, you get that it is a structure, but actually it's a mechanism because of special geometry. Uh, there there was an example of a double parallelogram mechanism. So because of very special dimensions of the mechanism, it turns out that it was a mechanism, but the degree of freedom calculation tells you that it's a structure. So the dimension of the links, the dimensions of the links is sometimes important, but that is not there in the degree of freedom calculation. So you will have to be careful. So the reason we discussed it, that you should have this idea that this degree of freedom calculation may fail under various conditions. And there was another third condition under which it fails, is when you have 3p loops. And so 3r has 0 degree of freedom, which is what you get from the degree of freedom calculation, but 3p will have 1 degree of freedom. So whenever you see a 3p loop, you have to add 1 because that allows 1 degree of freedom. So there are these special situations where the degree of freedom calculation might fail. So you'll have to take extra care for such situations. Then we came to the most important and very interesting and most beautiful result in possibly all of kinematics, kinematics of mechanisms, which is the Grashof criterion. We have seen how this thing works. So what is the basis? Why do we need this criterion? So Grashof criterion tells us whether there is a link that can rotate completely in a kinematic chain, say a 4R chain or a 4-bar chain, whether there is a link which can rotate completely with respect to all other links. The reason for this question arises because you see mechanisms are driven by rotary motors. In very many cases, they are driven by rotary motors. So we would like to know or design a mechanism in which one link which will be connected to the motor can rotate completely. So what kind of dimensions of the or dimensional condition should you have so that one link can rotate completely? Grashof criterion tells us that if the length of the minimum length, that is the shortest length of the shortest link plus length of the longest link, if it is less than the sum of the other two link lengths, then this 4-bar chain or 4R chain, in this 4R chain, the L min, the link with the shortest length, will rotate completely with respect to all other links. Now, depending on which link you are grounding, the behavior of the mechanism will change. For example, if you ground a link which is adjacent to the shortest link, then you will get a crank rocker mechanism. And it is known as the Grashofian crank rocker mechanism. And you remember that in a Grashofian crank rocker mechanism, the rocker cannot cross the line of frame. And there are hence two assembly modes, two modes in which you can assemble the mechanism. Whereas if you fix the shortest link itself, then it becomes a double crank mechanism. If you fix the link opposite to the shortest link, you get a double rocker, a Grashofian double rocker mechanism. And in the Grashofian double rocker, as you know, the rocker cannot cross the line of frame. So with the Grashof chain, you have these many possibilities. If you have non-Grashof chains, which means chains which do not satisfy the Grashof criterion, then you have all double rockers. And then you can have in a non-Grashofian double rock. Non-Grashofs are all double rockers. So all double rockers, non-Grashof chains, the rocker can cross the line of frame. And there is a unique assembly mode. There is only one assembly mode. So that way it's different from the Grashof chain. You can have the swing angle or the range of swing of the rocker as in, which means both the rockers, they swing within the base link, or out or in out. Okay, so the swing of the rocker, the rocking angle, that it can go as in, which means both are inwards. It will cross the base link. And out means both will be outward. It will cross outside the base link. So these are the possibilities in a non-Grashof chain. So Grashof chain is a very important, Grashof criterion is very important. And then we extended this Grashof criterion from 4R mechanisms to 3R1P by using this idea of metamorphosis. And we found that the Grashof criterion for 3R1P is slightly different. So L-min plus the offset, and we have I have defined what offset is uh, in the lectures, and in multiple places I have defined how you can find the offset of a 3R1P chain. So if L-min plus the offset length is less than the length of the third link, then it's a crank rocker mechanism, else it is a slider rocker mechanism. So the link that can rotate completely is known as the crank. So after discussing this Grashof chain in the second week, lecture number 9, we discussed about geometry and representation of vectors. This is just uh, some basic discussions on how to represent vectors, etc., and doing some very elementary vector operations, dot product, cross product. Right? So because this geometry of vector representation and their uh, decomposition of vectors, etc., these things are very important in kinematics. Then we started off with the displacement analysis of constrained mechanisms. Uh, in in week 3, we continued with the displacement analysis, and we have discussed two kinds of problems in displacement analysis: forward kinematics and inverse kinematics. And we have discussed the 4R chain, the 3R1P chain of two types. Uh, and and whenever we discuss this inverse or forward kinematics or direct kinematics, we have come across this equation of the structure A sine theta plus B cos theta is equals to C. This is central in displacement analysis, and you should try to go through the derivation. I have gone through the derivation or the solution of this equation at multiple places, because this is a very important equation and it comes up in displacement analysis, and you should be able to solve this equation confidently. So A sine theta plus B cos theta is equals to C. And how we solve, we go over to tangent of the half angle and convert this equation. So this is a transcendental equation, a nonlinear equation, and we convert it into a polynomial equation, a quadratic equation, using the properties of trigonometric identities. So this transformation is very important, and you should have a good practice of the solution. And since it's a nonlinear equation or it's a transcendental equation, we find multiple solutions. And in all this displacement analysis that we have discussed, I have shown you geometric interpretation of these multiple solutions, how these multiple solutions can be understood geometrically, graphically. Then we looked at the displacement analysis of open kinematic chains, which means basically robots, serial robots. And this went on to the fourth week. So we are currently in the fourth week, and we are discussing open kinematic chains. And then we will go over to closed chains, which means parallel manipulators, which is a very important manipulator robot structure, which is of great use in industry. You see, serial manipulators or serial robots, uh, their load carrying capacity uh, is limited because it's the chain has to carry the weights of the distal links one after the other. So it's serially connected, and we try to avoid mounting motors at the distal end of the manipulator, so that that additional load doesn't come on the base motors. We try to, but it's not always possible. But these serial manipulators, first of all, their robustness and their load carrying capacities are much lower than parallel manipulators. Parallel manipulators are very robust, and since all the prime movers of the motors are directly connected to the uh, end link, which is a singular link, and which actually carries a tool or something. So you will find parallel manipulators, use of parallel manipulators uh, to be, or closed chain robotic systems being used in machine tools because they are very robust. They can deliver higher forces, torques, etc. And hence their dimensional accuracy or uh, their repeatability will be much higher, but their kinematics may be a little more complicated. We have seen that in serial manipulator, the forward kinematics is very simple. On the other hand, in parallel manipulators, the forward kinematics is a little more tricky. The inverse kinematics is simple. So this week we are discussing about displacement analysis of closed chain robots, and I would uh, request you to give particular attention to this, and particularly displacement analysis of constraint mechanisms, uh, open chain robots and closed chain robots. So these are some of the things which we have covered till now, and I hope that you are having a smooth sailing with the course. If you have any issue, any doubt, or any question, right now you can put through the chat box, or you can access the spreadsheet which has been shared with you. And if you have questions for the later, you can always ask in the forum, and our teaching assistants who are taking care of the uh, running the forum and taking your questions, they will get back to you. If you have any difficulty there, please write back. We will take care of your uh, query. And if you are a teacher in a college, please let us know how your students are benefiting from this course. It will be great feedback for us, and we will try to uh, address some if you have some issues. So, with this, maybe we can close this session since there are no questions. We can close this session. I would like to thank the TAs in this course and the NPTEL staff, NPTEL office staff who made it possible to hold this live session. So thank you, and looking forward to receiving your queries and feedback. Thank you.